is because this is sort of important for everybody to hear. At the end of your EPA manual, there is a temperature pressure chart. Under normal circumstances, what I would do is I would actually give that out to you guys on paper if I was in the classroom. Unfortunately, as you know, that causes a little bit of problem right now because I don't really have a way to give it out to you on paper. So you have the ability to use that temperature pressure chart while you're taking your exam. That's the only thing that I'm allowed to have that you can have out with you is a temperature pressure chart. The ones that came in your tool bag, for those of you who have toolkits, do not contain the new refrigerants that are going to be talked about in the temperature pressure chart. So I would recommend that you print that temperature pressure chart that's at the end of your EPA manual. Now, I know some people do not have access to the printers. So I would figure out a way to open that on a cell phone or something like that. And my reason is for saying this is you can't switch screens on your iPads or whatever device you're taking the test on. You can't switch screens in the middle of the test, okay? That's going to cause a problem. So you just have to make sure that while you're taking your test, okay, you have a way to look at that temperature pressure chart. Does anybody have any questions on that for me? Okay, I will also put the temperature pressure chart, I'll put an announcement up here after our class today, and I'll put another copy of that temperature pressure chart up there, just the chart itself. Might make it easier for you to print, okay? So I'll throw another copy out there, just the chart itself, so that we give that to you. But again, you're going to be allowed to have, when you take your EPA exam, what they're allowing you to have is the temperature pressure chart, some scrap paper, okay, and you're going to have to hold it up to your device's camera and show that it's blank. You're allowed to have something to write with, and you're allowed to have a calculator. I'll let you guys use your cell phones as a calculator or whatever. That's fine. But once you're in the test, okay, you can't switch screens on your iPad. It reports that you switch screens, and it's just going to cause a problem. It's going to be a bad thing. Any questions? Okay. Your EPA proctors, the instructors doing the proctoring, should have already started reaching out to you. If you don't hear from them by Monday, I need you to let me know. Just send me an email. Okay, if you don't, actually let's say by Friday, if you don't hear from them, send me an email and let me know you haven't heard from them, okay? I sent the rosters out yesterday afternoon to the assigned instructors, so you watch your emails, and it's going to be your school email. Okay, watch your emails because that's how they're going to contact you to set up at a time and a date to take your EPA exam. Okay, and I know some have already started reaching out. So, and if you can't make the time that they scheduled, just politely say, can you pick another time? There's nothing wrong with that. Ask them, give them a reason, and just ask them if you can pick another time, because you need to be able to be uninterrupted while you're taking your EPA exam. Can't have any noise in the background. Okay, I want to talk about heat pumps today. What can anybody tell me about how heat moves? Give me an idea of how heat moves under normal conditions.
It always moves to the colder area.
Heat always moves from hot to cold, naturally. What can you tell me about the evaporator and the condenser? How do we get heat to move into the evaporator and out of the condenser?
For the evaporator, it has to be colder than the area that you're trying to cool, and with the condenser, the outside like ambient temperature has to be cooler than the condenser.
Okay, and that is correct, but let's narrow that down a little. Let's narrow that thought down a little bit further. Okay, how do we cause that to happen?
With a differential.
Okay, so in other words, we raise our pressures, which raises our boiling point on the condenser, right? And we lower our pressure, which lowers our boiling point on the evaporator. Okay, so all we're doing is changing our pressures around. Is there any reason why I couldn't do that in reverse? Change the coils around. Make my indoor coil the condenser and make my outdoor coil the evaporator. Is there any reason that wouldn't work? That's what we're doing in heat pump, folks. So heat pump systems, okay, they lead all other forms of heat in terms of efficiency and low operating costs, and I'll explain more about that. But they actually put off more heat than the amount of energy that you're putting into it. There's only two forms of heat that are 100% efficient. There's only one version of heat that is over 100% efficient. Okay? Heat pumps is over 100% efficient. What's the other form of heat that's 100% efficient?
Electrical heat?
Electric heat, yeah. Okay, so electric heat is 100% efficient. Heat pumps are over 100% efficient, again, because of the fact that we absorb heat in the refrigeration cycle. The demand for heat pumps has increased drastically over the last couple years because of the cost of all forms of energy. When they're installed correctly, okay, we can take advantage of their energy-saving technology. The problem is, a lot of people don't understand heat pumps, so they don't get installed correctly. Okay, again, heat pumps derive their name from the manner in which heat is being delivered to the home. It's not producing heat. It's actually pumping heat from one area to another. We always have heat in the outdoor environment. Okay, when we're down to, I think it's like 0 degrees Kelvin or something like that, is where we lose heat at absolute zero. Anything above absolute zero, we have heat. Now, heat pumps basically can use heat anything above 32 degrees. Now, why is 32 degrees a magical number if I switch the indoor and the outdoor coil? If all of a sudden my evaporator is outside absorbing heat, why do I care about that 32 degree mark?
In winter.
Yeah, but why do I care? Yeah, it would be winter. But if my evaporator goes under 32 degrees, what happens?
Starts to freeze it.
Starts to freeze up. Okay, starts to freeze up. So, yes, a heat pump will work under 32 degrees, but once that evaporator starts to freeze up, I have to go into a defrost mode. Okay, and I have to melt that ice off that evaporator coil. So normally, we try to use heat pumps in an environment or during the time of the year where the evaporator doesn't go under 32 degrees, which is the outdoor coil. So they're not producing heat, but it's just pumping heat. The efficiency is rated in not how efficiently they consume energy. Okay, I don't care about the efficiency in terms of it's using this much energy. I care about how efficiently it's moving heat, moving energy, which is a form of heat. Okay, the first heat pump, believe it or not, was developed in 1852. Okay, it isn't at all what it looked like right now. But the first heat pump was developed in 1852, so it's old technology that's been modernized over the course of years. Now, if you're in an apartment building, and if you have an air conditioning with electric heat, or in a condo, or in some residential buildings, okay, you might have air conditioning, but a lot of times you're using electric heat during the winter months and your power bills show it. Heat pumps generally cost a third of what it costs to operate with electric heat strips. Okay? So again, you replace that air conditioner with a heat pump and you can cut your power bill in a third. okay, on average, if you don't have gas or oil in the house. It's something big that a lot of people who own condos are starting to look into because it's so important in terms of energy efficiency. The first heat pump, Scotland in 1927. Again, not new technology, old technology. Okay, between 1927 and 1950, heat pumps were extremely popular throughout Europe, southern parts of the U.S. Many were simply air conditioners that were converted to heat pumps by the addition of a reversing valve. We're going to talk very heavily about the reversing valve before the day is over. Okay, the reversing valve becomes very important. The early heat pumps often failed because they did not have defrost. Okay, in other words, once the coil started heating up, okay, once the outdoor coil started freezing up, it grew ice. When we grow ice on the evaporator, we start sending liquid refrigerant back to the compressor. There were no crankcase heaters, and there were no suction accumulators. Remember, I showed you the diagram when we were doing the EPA of a suction accumulator. The suction accumulator, all it's there for, it's a tank that's designed not to send liquid refrigerant back to the compressor. Although improvements in designs were made, making them more reliable, the early failure rate still caused problems in the market for years. People wouldn't install them because everyone said heat pumps sucked. Okay, because there was a reputation that they're not working properly. Okay, today, okay, and when you get out in the field, most air conditioners that are installed should be heat pumps. Okay, there's a reason for this. It's because of economics and environmental issues. Think about it. If I can, in my shoulder seasons, I call that the late summers, the early falls, and the late springs, as soon as my outside temperatures start getting up over 32 degrees, if I can be using the heat pump instead of fossil fuels, instead of electric heat, A, I save money, and B, there are some serious environmental impacts. My heat pump runs great off my solar. Okay, so I very rarely actually pull power from the grid during the daylight hours to run my air conditioning, which is also a heat pump. Okay, so a lot of times heat pumps and solar and heat pumps and wind energy can all work together to keep electric bills down. It's energy conservation. Okay, so again, we can eliminate a lot of energy use in a lot of buildings by using heat pumps. And again, anything from, I want to say, southern Connecticut south is where we're starting to see heat pumps being used more and more heavily.
Is that a standard feature on a lot of ACs you buy?
No, you have to specifically buy and order a heat pump.
Okay.
Okay, it's not a standard feature, but the contractors who are really working with their customers, they are now offering it as options. Okay, because again, it's something that can be put in addition to, it can be put in along with a fossil fuel furnace or something like that. I'm going to mute somebody here.
And how much extra does it cost normally?
The last time I had to price one out, there was a $300 price difference on cost.
That's not bad at all.
So my cost was about a $300 price difference, which from a contractor perspective, by the end cost to the customer, if the contractor's doing the right thing for the customer, it may be a $500 difference.
So is a heat pump something that you would only really want to put on a split system, or is it something that window units could also get?
There are heat pump window units out there. Yes, there's heat pumps in just about every configuration at this point, and I think I'll show that to you later in this slide set. Okay, like refrigeration systems in air conditioners, heat pumps transfer from one place to another by changing the state of refrigerant. Okay, basically all refrigeration systems are heat pump. They transfer heat from a heat source at a low temperature to a heat sink, which is what we call the outdoor environment, at a higher temperature. What makes the heat pump unique is the ability to reverse the direction of refrigerant flow. This is the very important part of this, guys. Okay, heat pumps are different from air conditioners because we have the ability to reverse the direction of refrigerant flow. That's the biggest difference with heat pumps. I can change the direction of the flow. In the summer, it removes heat from the inside air and moves heat to the outside air. In the winter, it removes heat from the outside air and moves it to the inside air. Heat pumps are also referred to as reverse cycle refrigeration systems. You'll see that terminology on occasion. Reverse cycle refrigeration systems is a heat pump. Okay, some basic things we have to understand. Heat exists, as I mentioned, down to absolute zero, which is negative 460 degrees Fahrenheit. Heat will only flow from a higher temperature to a lower temperature. Okay, we know that. We've talked about that a number of times. Heat only flows from high to low. Gases become warmer when they're compressed. We have a change of state. Most things, most matter, can be a solid format, for example, ice, a liquid format, which is example water, or a gas form, which is steam. The temperature at which a material changes from a liquid to a gas or a gas to a liquid depends on the pressure at which it's contained. That's why we can raise the pressure, which raises the condensing point of the refrigerant in the condenser coil. One of the biggest obstacles to overcome for most people with the understanding of heat pump is to accept that heat exists at very cold temperatures. Okay? We have heat outside at all times until you reach absolute zero. Now, usable heat is at a slightly higher temperature, but there's heat outside at all times. Heat will flow from a high temp to a low temperature. The job of this heat pump is to make heat flow from a cooler area to a warmer area. To do this, the heat pump, just like a refrigeration system, just like air conditioning, has a low side, which is colder than the cool area, and a high side, which is warmer than the warm area. Moving the heat from the low side to the high side is where the name pump comes from, because all we're doing is moving heat. The high side is created by compressing or squeezing the gas, just like we do in a standard air conditioner system. And that's by the compressor. Then on the other side of the system, we expand that compressed gas or liquid. The pressure and thus the temperature will drop. That's done by the expansion valve. So in a heat pump system, just like an air conditioning system, the compressor compresses the gas, raising the pressure and temperature. The expansion valve expands the gas, lowering the pressure and the temperature. It's possible to build a heat pump just by compressing and expanding the gas. A change in state of the refrigerant will increases this efficiency. Liquid absorbs about 100 times more heat when they change state than they do when they change temperatures. That's why the latent heat change is so important. Okay, that latent heat change, which is liquid to vapor or vapor to liquid, okay, it does about 100 more times heat exchange than when they just change temperature, which is sensible heat. So again, latent heat is the important step of this whole process. Okay, so the refrigerant evaporates from a liquid to a gas in the evaporator, and it condenses from a gas to a liquid in the condenser. By now, everyone should know this. The temperature at which evaporation and condensation takes place is controlled by pressure. That's the only reason I care about pressures, is it tells me the temperatures of the evaporation and condensation. Okay? The increase in pressure on the high side raises the condensing temperature, allowing the condenser to reject large amounts of heat while condensing the refrigerant. The decrease in pressure on the low side lowers the evaporation temperature, allowing the evaporator to absorb large amounts of heat. The biggest obstacle with heat pumps for the end customer, and this is important, is that it has a cooler supply air temperature. Okay, the temperature of the supply air that's being blown into the space is cooler than what we get from fossil fuels. Okay, many customers have become used to the traditional furnaces. Okay, typical heat pump only supplies air temperatures between 95 to 110 degrees Fahrenheit. That's our supply air temperature, so it's just slightly above or at body temperature. Electric heat has a discharge of 110 to 125 degrees. In fossil fuel burning equipment, the supply temperatures reach from 120 to 140. Okay, so heat pumps is a much lower supply air temperature than normal. Okay, however, even though you don't feel this 120 degree air blowing on you, okay, it doesn't mean it doesn't exist. Okay, so I may not feel that 120 degree air, but if I'm blowing 110 degree air into a space that's 65 degrees, that space is going to heat up. Okay, it might just not feel it to the customer. Anybody have any questions on this slide? This is sort of important. Okay. 95 degree air blowing across the body in the middle of the winter has a tendency to feel drafty. The solution to this is we're very careful where to place supply registers. Supply registers should not blow directly on the occupants. Heat pumps are designed to heat the space, not the person. Heat pump source is where the heat comes from when the heat pump is in the heating cycle. Traditionally, the source can be the air outside, or it can even be water. Okay, we have something called an air-to-air heat pump that takes the outside air and absorbs the heat from the air and pumps it off into the inside air. We also have water-to-air heat pumps. They're otherwise known as geothermal units. Okay, we absorb heat out of warm water or warmer water, and we move it into the inside air. So air source heat pumps will pull heat out of the surrounding air. Water source heat pump will pull heat out of the water circulated through them. Two different types of heat pumps, but they still have the same identical operation, basically. One's pulling heat out of the water, one's pulling heat out of the air. But the refrigeration cycle for this is still the same. The heat sink is where the heat pump puts the heat. The heat sink is often assumed to be air, since most heat pumps are designed to condition the air in a space. Couple examples. The water source heat pump only mentions the source because the sink is assumed to be the air. However, there are water-to-water heat pumps that use water both as the source and the sink. But if you hear the term water source heat pump, it just says we're pulling heat out of water and we're moving it to the air. Okay, if you see water to water, it means there's water on both sides. So again, the heat sink is always assumed to be the air unless you're told differently. So we have a couple different types of heat pumps on this table. Okay, so if the type of unit is called an air source heat pump, the source of the heat is the outdoor air. The sink, which is where the heat is going, is the indoor air. We use it in homes, okay, most homes and small businesses, okay, that heat and cool with forced air. We also have water source heat pumps, otherwise known as geothermal. The source for the air is groundwater, or the source for the heat is groundwater. And again, we move that heat to the indoor air using a coil. And again, homes, small businesses. We have air-to-water heat pumps. The source is the indoor air. The sink, which is where the heat is moving, could be a domestic hot water tank. Okay, you have a water heater with a compressor sitting on the top of it. Okay, it's always set into what we call heating mode. So the evaporator, which is now on the compressor, on the condensing unit, absorbs heat from the air and it puts it into the domestic hot water tank to maintain about 130 degrees on the domestic hot water tank. Extremely efficient units. Water-to-water heat pumps use the groundwater, okay, or ground water that's being looped through the ground as my heat source, and it might put it into what we call a water loop, where you might use it with, let's say, radiant heat in your floors to heat the home or small business with hydronic radiant heating. Okay, so these are your 4 types of heat pumps that are seen most often. Now, anything that uses groundwater on this chart as a source, it could also be a water loop in a large commercial building. Okay, in other words, we may loop water through a large commercial building like a hotel, where every room has independent control over whether or not they want heating or cooling. And depending on what the room chooses, the temperatures and so on and so forth, the compressor in that heat pump unit either absorbs heat from the water or puts heat off into the water. So the groundwater could also be exchanged with a water source. Any questions? Okay, heat pump come in different configurations because they match many different applications. We have packaged units, we have split systems, and we have ductless mini splits. By the way, I count as packaged units include things like the PTAC units in hotel rooms that have individual controls. Also include window units because you can get window unit heat pumps. I've seen some even at Lowe's recently. Package units come with all the system components assembled together in one package. Okay, there's units that are made for outdoor installation. There's units that install over drop ceilings. There's units that are through the wall or mounted on a wall. Okay, the larger ones, the traditional package units, okay, sit outside. Okay, they can be on a roof, they can be sitting next to a house, they can be sitting next to a mobile home. That's what I see a lot down in this area. They're sitting on the ground next to a lot of the mobile homes that are down here. Okay, package unit. Entire unit is designed to sit outside. This is a horizontal water source package unit, again, installed above a drop ceiling. They're compact and they fit into small spaces above the ceiling. Okay, now what we do in this type system, again, we mount the ductwork to where the blower fan is. So this is a water to air heat pump, and we loop water through 2 lines coming in and out of the unit. One of them is in and one of it is out. In here, there's a compressor and a heat exchanger. So again, water to air, or just a water source heat pump, but again, mounted over ceiling.
Have you ever seen a heat pump for a floor unit?
What, for what again? For
a floor unit.
So for a floor, it's in the floor?
No, like a one of the standalone air conditioners that you mount in like your living room. That has the hose that goes out your window.
Oh yeah, okay. So one of the portable ones?
Yeah.
I have to say I've never seen it in that configuration. I haven't seen it in that configuration at all.
Yeah, I was just curious. We happen to have one of those. That's how we cool our living room, is one of those.
But I'm wondering how much heat that thing would give off. If you
it gives off heat.
Yeah, but I'm just wondering how much heat that would give off if you just recirculated that air right into the same space.
Yeah, that's actually an idea, because it puts out heat. That exhaust is putting heat outside.
Because you do have a heat gain.
Well, they definitely make portable units that have heat pumps in them.
Yeah, I haven't seen it. Where have you seen one of those?
Last I researched portable units online, every one of them that popped up had the heat pump option on them as well. They're rather expensive, but the new ones, it seems like they're starting to do that now.
Okay. Yeah, I haven't seen any of them, so again, it's something that I'm not that familiar with. So, but if they're out there, It's actually a good idea.
Yeah, I know a lot of them now also duct with 2 separate hoses. That way it doesn't room into a negative pressure also. So
that's the one. That's the one downside with a lot of the older portable units is they suck that house into a big negative pressure. So, Dylan, I think you were the one who said you have one in your living room. That's one of the problems with those. If you don't have 2 hoses coming in and out of that, if it isn't a double hose, believe it or not, you're actually pulling all your conditioned room air and you're sending it outside because of that. That's how it cools the condenser coil that's in there. It pulls your room air and it pushes it outside. So you're spending a lot of extra money cooling that space.
It also draws a lot of current.
Yeah. But you're actually spending, because somewhere around your house, it's pulling air in through cracks and crevices to make up for that air. So it's really not cooling that room. Well, it's cooling the room so you feel it, but it's taking a lot of extra power.
Yeah, it's probably something I'm gonna have to replace.
I looked at that when I have a room here in my house that doesn't cool properly, and before I took care of the ductwork issue that was causing it, I looked at those and I was like, no, I'm going to put the house into too big of a negative pressure. So I actually broke down and threw in a window unit till I could get the repairs made. Okay, moving on. Sorry, I can't really answer that question myself, but someone else did answer the question, so that's a good thing. But again, above ceilings, you see these in commercial buildings very heavily. Okay, package terminal units. These are designed to fit through a sleeve in a wall, like in a motel room. And I've also seen these in some houses recently where people have put these into outside walls in houses. Okay, these are heat pumps, very efficient units. Okay, when they're in a motel room, you think, oh, it's a cheap thing in the window because it's always noisy. But if they're maintained properly, if they're taken care of, these are extremely efficient units. You see wall-mounted package units also as vertical air source heat pumps that bolt directly to the wall. Sometimes for large open meeting rooms, I've seen them used in convention centers, I've seen them used in computer rooms, and I've seen them used in cell towers. Okay, basically pumped directly to the wall. So the top side of this is where we have the air exchange from the inside. Bottom side of this is where our outdoor air exchange is. All your compressor and your controls are normally in the center there. Again, extremely efficient units, but they're normally installed on you see them a lot on where there's cell towers and other stuff sitting in the middle of a field someplace. Split systems. All they do is break the unit into 2 separate components that are connected through refrigerant lines. We've talked about these before. Okay, as an indoor unit and an outdoor unit in a line set. The outdoor unit houses the compressor and condenser coil and metering device and reversing valve and a lot of the system controls. The indoor unit has the blower, the evaporator coil, and a metering device. Oh, wait a sec. I said 2 metering devices here, right? One thing about a heat pump. 2 metering devices. Okay? We have to meter refrigerant flow in both directions. So this is an example of a split system heat pump. Okay, this was an Amana picture I grabbed from someplace. The one thing about heat pumps, okay, you have a lot of controls, a lot of electrical, and you have to have a secondary form of heat. You can mount a heat pump along with an existing gas furnace. You can mount a heat pump along with an existing oil furnace. But if you don't have either, you have to have a backup form of heat. And in this case, this is showing it's electric heat strips. Anybody know why I have to have a backup form of heat? What happens if my outdoor temperature drops below usable temperature that the heat pump can really efficiently pull heat out of? It can't maintain anymore. Okay, I have to have a secondary form of heat. Ductless mini splits, heat pumps. They're awesome heat pumps. Okay, they're split systems, but they don't work with ductwork. Indoor unit is designed to be installed in the space being conditioned. There's mini splits that are available that can connect up to 8 indoor sections to a single outdoor unit. In other words, you can put an indoor unit in an indoor part of this in about every room in the house, okay, providing individual zone comfort control without ductwork. And you can have one outdoor unit. All the line sets run to that outdoor unit, and it's all based on refrigerant flow and who is calling for heating or cooling at one time. Okay? Heating always takes priority over cooling. When you have multiple units, heating always takes priority over cooling. The metering device, when you have a mini split system, the metering device is only located in the outdoor unit. And this is also important for air conditioning mini splits. The mini split, the metering device is only in the outdoor unit. Both of the lines, okay, going to the unit, going to the indoor unit from the outdoor unit should be insulated. Okay, regardless of what mode the unit is in, the refrigerant is passing through this metering device. Okay, so again, with ductless mini splits, the metering device is only in the outdoor unit. And this is also with ductless mini split air conditioning. This is just an example of what we're talking about with ductless mini splits. Okay, this is an older picture. They've come a long way since this picture. I have seen recently some ductless mini splits installed that the flat screen TV on the wall over the fireplace is actually a mini split air conditioner. Okay, they're now hiding them behind picture frames. You can hide them under appliances. You can put them just about anywhere so they're not obvious. Why are ductless mini splits? Can anybody tell me why mini splits are so efficient? What's good about them in terms of efficiency? I think someone in this class has ductless mini splits. Can you tell me why it's so efficient?
I do.
Yeah, why are these so efficient?
Because to be honest, I don't know. Unless, except for, I'm thinking maybe without all the duct work that's going through the house.
Oh, you're thinking 100% correctly. Yeah, I have no duct loss.
Right. So, but yeah,
Okay.
I got 3 of them in my house total. My one downstairs, and it cooled the whole downstairs, and then 2 that kind of cross each other upstairs. So they work pretty well.
Got me thinking you also have multiple evaporators on the same condenser, which is kind of cool compared to most other systems.
Yeah, I really, if I had to do my house all over again, okay, if I were building new construction, I would 100% be looking at ductless mini splits. I wouldn't do any duct work, because when you run duct work through an unconditioned space, okay, you have heat loss and heat gain on the ductwork itself.
How much does a system like that cost?
Should about $6,000, right?
Well, installed, my cost on these systems is a whole lot less.
It all depends on how many indoor units you're getting, and
yeah. Let me see if I can pull something up.
Even though you say that's cheaper, sometimes the vents, the ductwork makes it look better because you can't. I mean, you can hide the wire, but it looks better if you can't see it at all.
Well, like I said, my system is 17 years old, so I've been looking for something new soon. And I've been thinking about these.
Yeah, I'm
trying to, guys, I'm not ignoring you. I'm trying to pull something up real quick in another window. Just bear with me a sec.
I like the mini split system a lot, but
in your house, Chris, do they have the covers for the hoses, or is your hoses inside the wall?
my hoses go right through the wall and then down the side of the house, and my house has vinyl sidings, and they made a vinyl cover for the pipes as well. So it looks pretty good.
Now, can you run all of the units to one condenser, or do you need multiple condensers?
All to one.
I have two indoor units that go to one compressor outside, and then one that goes to another one on the other side of the house. So you can do 2 to 1.
Okay.
Do you have the water drain going into your slop sink in your basement?
No, it drains outside. There's drain tubes that go outside.
Okay.
Okay, just to give you an idea, okay, I'm pulled up my pricing locally, okay, from the supply house I use here locally. Single wall mounted ductless heat pump system, $395 is my cost.
Just for the system though, right?
That's for that's for your outdoor and indoors. That's a single zone. Okay.
Do you have something with like 3 or 4 of the?
Let me.
Just curious.
Let me see if I pull up multi-zone.
What's your price for installation, Chris?
What?
What do you charge for installation?
I've gotten old enough I don't do any installations anymore.
Okay.
But these you're gonna pay a couple thousand for installation unless you do it yourself. Multi-zone. Okay, this one. This is just the outdoor unit. It handles up to
27.
Looks like it's four zones. It can handle up to, I think. And it's priced out is $1,295 cost.
That's the heat pump too. Mine only does air conditioning. The one
That's the heat pump. Now you got to, along with this outdoor unit, you have to buy the number of types of indoor units you want to go with it.
Mm-hmm.
Yeah, I had just been looking online the other day, and I saw some prices on packages. Now, I don't know about the brands at all. They were probably from the cheaper suppliers. But I saw a few that were in the like $2,000–$3,000 range for the condensing unit, the whole package, and like maybe 3 evaporators.
Yeah, I'm not going to pull up Amazon because on a video call because I really don't want to broadcast my Amazon account and everything. But I'm going to tell you right now, some of the pricing I've seen on Amazon recently for the mini splits has actually been pretty good. Now I'm very careful on online stuff because believe it or not, there's a lot of things being sold online that are European models. Okay, now what's the difference between the United States and European models?
That would be the frequency.
And voltages.
Yeah, stuff's not really going to work properly.
Yeah, there's usually a problem or two when people install those. That comes down to pay me. That call falls under my pay me now or pay me later category with customers.
So I just looked one up at 42,000 BTU, 3.5 ton for 5 units with a condenser. It's $3,400.
5 units with a condenser?
Yeah, $3,400.
What's the brand?
Hold on.
Yeah, I'm getting a little off topic here, but what was the brand?
Blue Ridge.
Never heard of them.
Yeah.
Well,
they're on Alpine Heating.
I don't know how they are, but
yeah, I've never heard of them. So, but I'm going to tell you the other thing though. If you research into the brands a little bit, you're going to find out that the brand names a lot of times are actually, like, for example, Mitsubishi makes 4 sub-brands of different names. Okay, so if you research back, you're going to find out that a lot of these off-brand names that are being sold to the general public, just like that, are actually made by some pretty major brand names. But because of their agreement with the dealers, with the contractors, they don't want to sell it under the brand name. They can't. So they sell it under a sub-name. Okay, if that makes any sense whatsoever. So, for example, Carrier sells air conditioners under 5 different sub-names. They'll never sell a Carrier model to the general public, but they'll sell one of their sub-brands directly to the consumer. So a lot of these direct-to-consumer stuff, you're actually getting some pretty decent brand name material. You just have to trace it back. Okay, any questions on that? Okay, moving on. This is a heat pump hot water heater. Okay, I have one of these sitting in my garage. Has a compressor and everything, evaporator up top. Okay, sucks the warm air in that's always in my garage and puts dehumidified cool air out. Okay, I get 2 benefits out of this sucker. Okay, one benefit is I get really nice hot water supply. Okay, that's always there. My other benefit is it cools and dehumidifies my garage, which is where my workbench and everything is. Okay, sort of some nice benefits on that one. But the heat pump hot water heater, really like it. It's actually cheaper to operate than a gas or electric water heater is. Okay, so those are the different types of heat pumps. Now, I do want to talk a little bit about what makes this work. But before I go on, does anybody have any questions on the basic operation? Basically, what a heat pump does. Okay, let's talk about the heating and cooling cycles of the heat pump. Okay, again, we're moving against a temperature rise. In the summer, they move the heat from the inside to the outside. In the winter, they move the heat from the outside to the inside. The direction of heat flow is controlled by the direction of refrigerant flow. Let me say that again. The direction of heat flow is controlled by the direction of refrigerant flow. Now, let me make this very, very clear. We do not reverse the direction of the compressor. The compressor always runs in the same direction. We just reverse the flow of refrigerant after it comes out of the compressor. In the conventional refrigeration cooling cycle, heat is absorbed by the evaporator, which is the inside, and discharged to the outdoors by the condenser. To change from cooling to heating, the indoor and the outdoor coil need to trade functions. The outdoor coil becomes the evaporator. The indoor coil becomes the condenser. Let me repeat that. In the heating mode, the outdoor coil becomes the evaporator. The indoor coil becomes the condenser. In the heating cycle, heat is absorbed by the outdoor coil, which is now the evaporator, and discharged to the inside by the indoor coil, which is now the condenser. So in a heat pump, we do not label evaporator and condenser. Okay? If you look at a heat pump manual, you are not labeling anything evaporator and condenser. You are labeling indoor coil and outdoor coil. Because at heat pump, we don't have a single evaporator or a single condenser. It's dependent upon the mode of the system. Is it in heating or cooling mode? So in a conventional cooling cycle, this is traditional air conditioning. This is the same refrigeration cycle we've been working with since day one of last course. Okay? High temperature pressure vapor comes out of the compressor, goes through the condensing coil, desuperheats, condenses, subcools. We're in the liquid line. as a liquid. We go through the metering device, come out of it as a low temperature, low pressure liquid with flash gas. We boil it off as it reaches the saturation point, and then we return it to the compressor as a low pressure vapor. That's our cooling cycle. Condenser coil is our outdoor coil. Indoor coil is our evaporator. In a heat pump, we add an additional device. So when you look at this diagram here, we have an additional device on the heat pump. Okay, we've added a reversing valve. Okay, so we come out of our compressor. We come through the reversing valve to my outdoor unit. This is in cooling mode. Okay, we come out of the compressor, through my reversing valve to the outdoor unit. We discharge heat to the outside. We come back with our liquid line. Okay, and we go through our bypass valve. Okay, we're no longer, this is an extra metering device, just so you know what that is. We're not going through the metering device there. We go through the metering device as we go into the evaporator, which is my indoor coil. We do all the things the evaporator does. We come back through my reversing valve, and we come into the suction line of the compressor. My compressor is not reversing direction. This is very important. The compressor runs in one direction only. We bypass the metering device that is not being used. Okay, we don't shove refrigerant backwards through the metering device. We bypass it. There's a check valve on those metering devices. Now, the coils of... Yeah.
Why is it there if it's not being used? Why not just delete it completely?
Because when I go into heating mode, which I'll show you in another couple slides, watch what happens to it. Because remember, my outdoor coil in heating mode then becomes the evaporator. So I have to use that metering device when it becomes the evaporator. Okay, because I have to drop that pressure. The coils of the heat pump, as I said, are typically labeled outdoor and indoor because they're dual purpose. This process is reversed by the means of the reversing valve that I just circled in the prior diagram. Now, this heat pump is in heating mode. Okay, so again, we're coming out of the compressor. Again, high pressure superheated vapor coming out of the compressor. The reversing valve now pipes that discharge to my indoor coil, which is operating now as my condenser. I de-superheat, I condense, I subcool. I come out of the indoor coil, I come through my now open check valve. Again, we're now bypassing the indoor metering device. I'm coming around through my liquid line, okay, and I'm not bypassing this extra metering device. I'm now going through this metering device to drop the pressure so my refrigerant can boil off and absorb heat in the outdoor coil. Because now I'm absorbing heat from the outside. And now this heat, this superheated vapor, now comes back through the reversing valve and into the suction port of the compressor, and the cycle starts all over. So this whole thing has to do with the reversing valve. The reversing valve is the heart of the heat pump system. Okay? We still have 2 points of pressure change, my compressor and my metering devices, whichever metering device is in the circuit. That's why we have to have 2 metering devices, because I have to boil off refrigerant for the outdoor coil in heating mode, because the outdoor coil is absorbing the heat and is acting as my evaporator. Now, This is the reversing valve. This is a close-up picture of the cutaway of my reversing valve. The discharge on my compressor always comes into the center port at the top of my reversing valve. Doesn't ever go anywhere else. Always comes into the center port. Okay? My suction side of the compressor always pipes into the center port on the bottom of the reversing valve. Okay, so my compressor always connects to 2 points on my reversing valve. Always. Okay? Then on the right side, when you're looking at it, looking at the coil, the right side goes to the outdoor coil. The left side comes from the indoor coil. And then connecting the two coils, one or more expansion devices and a filter dryer. It's very important that the filter dryer that's in that liquid line be reversible. Has to be able to be used in both directions. Okay, so all we're doing this reversing valve is we're using a valve that has multiple positions, and I'll show you these multiple positions in a minute. Questions on this so far? This is important. During the cooling mode, the high pressure, high temperature discharge gas goes from the compressor to the outdoor coil. Okay, again, to avoid restriction of the metering device connected to the outlet of the outdoor coil, a check valve is installed. This allows the liquid to bypass the outdoor metering device. Most metering devices don't work backwards. In the package units, you might find a bidirectional one, but most metering devices don't do well working backwards. The liquid travels inside the liquid line, where the indoor check valve closes, forcing the refrigerant through the indoor metering device. The indoor metering device drops the refrigerant pressure at temperature so heat can be absorbed. The refrigerant vapor produced in the indoor coil now travels through the reversing valve to the suction accumulator and on to the compressor. For the heating cycle, the refrigerant flow must be reversed for the heating cycle. However, the direction of the refrigerant flow through the compressor, as I've said 2 or 3 times, remains the same. The direction of the flow is reversed by the reversing valve. In the heating cycle, the reversing valve changes position, changing the direction of refrigerant flow. The high pressure temperature gas from the compressor now flows through the reversing valve to the indoor coil. The indoor coil is now the condenser, adding heat to the space. The hot vapor is condensed and the temperature is reduced to produce a high pressure, high temperature, subcooled liquid. The indoor check valve opens and allows refrigerant to flow to the indoor metering device. Continuing through the liquid line, the liquid is forced through the outdoor coil metering device by the closed check valve. The refrigerant flows through the outdoor coil, which is now the evaporator. The low pressure of that evaporator or the outdoor coil keeps the refrigerant temperature lower than the outdoor temperature, allowing the outdoor coil to pick up heat from the outdoor air. The refrigerant then flows through the suction line, the reversing valve, the accumulator, and back to the compressor where the cycle starts over. This is the heating mode. Okay, so again, our discharge of the compressor. The refrigerant comes out of the compressor, comes through my reversing valve as hot, superheated vapor, comes into my heat exchanger, which is my indoor coil, desuperheats, condenses, subcools, give off the hot air into the space. It bypasses the metering device, goes to my outdoor coil as a liquid through the liquid line. It's forced through the metering device because that check valve is closed. Okay? And it now boils off, and as it boils off, it absorbs heat, Once it's a vapor, it starts adding superheat, and it comes back as a vapor refrigerant through my reversing valve with that U and onto my compressor. That's the heating cycle. Indoor coil is now my condenser. It discharges heat. It's high pressure, high temperature. Outside coil is my evaporator. It's absorbing heat. When you feel the outside coil, the outside air coming off a heat pump, it is always cooler than the air around the heat pump. It's cold. We've absorbed the heat out of it. In the cooling mode, now look at this reversing valve. Okay, let me get rid of my pen on here. Okay, in the heating mode, look at how this reversing valve is. I have a direct flow through the reversing valve there, and I have a U on the suction gas there. Watch what happens in the next slide. The reversing valve changes position. So in the cooling mode, my discharge now goes to the outdoor unit first. This is standard air conditioning. But all that's going on is this reversing valve has a slide bar in here. This reversing valve changes position to change the refrigerant flow. Somebody has to have a question on this. Anybody? Okay.
Yeah, Chris. So you have basically two TSB in the suction line, right?
We have two TXVs on the liquid line. Okay? But only one is being used at any time.
So it's going the liquid line, not in the suction line.
Correct. TXVs only handle liquid. So one is being used, okay, in the heating mode, and one is being used in the cooling mode. We bypass it through a bypass check valve.
Yeah, I mean, the bulb that tells TSB how much.
Oh, the bulb. Okay,
yeah.
The bulb that's attached to it, yes, goes on the suction side. Always.
Both of them.
Yes. Well, but depends on the suction side for the mode it's in. Okay, so this TXV, the suction bulb would be mounted there. Okay, because it's not being used in the cooling mode. Think about it. The suction line changes. You see it? When I'm in heating mode, the suction line is what comes out of the outdoor coil.
Yeah, I see it.
Okay? When I'm in cooling mode, the suction line is what comes out of the indoor coil. Okay, so only one TXV bulb is really being used at a time. Yes, this bulb will heat up pretty hot in this mode, but this bulb is the one being used over on the left. Does that help?
Yes.
Okay. Any other questions before I dig a little bit into the internal operation of the reversing valve? Not going to go deep into it, but I do want to show a little bit of it.
Can you re-explain how it works, Chris?
The reversing valve itself or the whole cycle?
This presentation that you're on right now.
Okay, hang on one sec. Let me pull it back up. Let me get back to that. Just those two last slides?
Yeah.
Okay. So we have a heat pump that's it. Actually, let me do the cooling mode first. We have a heat pump that's acting as a regular air conditioner. Okay? Our outdoor coil is our hot coil. Our indoor coil is our cold coil. Okay? So when we have a regular air conditioner, we're coming out of the compressor. Okay, I'm coming out of the compressor, and I'm coming through the reversing valve with my discharge gas. I'm coming to the outdoor coil where I'm doing my normal thing a condenser does: de-superheat, condense, and subcool. I come out of the coil, but I don't go through the TXV that's on that outdoor coil. I bypass it through a check valve. At this point, I have a liquid refrigerant that is flowing in this direction towards my indoor coil and my metering device. This is like a standard air conditioner. I come through my metering device, I drop the pressure, I start boiling off the liquid refrigerant, I'm absorbing heat, because that's really what a boiling off refrigerant does, absorbs heat. I now have my superheated vapor. I come back through the reversing valve, and I come into my compressor suction line. Standard refrigeration cycle. With me so far?
Yeah.
Heating mode. Notice the change in flow of my liquid refrigerant down here at the bottom. Okay, my liquid refrigerant has changed direction. Okay, so coming out of my compressor, my discharge, which is hot, high temperature, high pressure vapor, is going to my indoor coil first. My indoor coil is de-superheating, condensing, subcooling. Come out of the indoor coil, I'm no longer going through the metering device. I'm bypassing it. The liquid bypasses that metering device and goes to my outdoor metering device, where I drop the temperature and pressure and start absorbing heat as I boil off this refrigerant and change it to a gas. Come out of the outside coil with the superheated vapor, and I come back through the reversing valve to the compressor. All I'm doing is reversing the flow of the refrigerant through the liquid line and through the coils. Does that help?
Yeah.
Okay.
Of course,
Yeah.
Can those reversing valves be put in wrong?
Say that again, sorry?
Valve, can they be put in wrong, like backwards?
Oh, absolutely. There's a lot of people who, when they have to replace a reversing valve, mess it up and put it in backwards. And if you ever have to change one out, just be very sure you don't put it in backwards, because there will be a whole lot of cursing and swearing going on. Okay, you put these things directly into the outside unit, and there's very little room to work. And if you put it in backwards, you have to cut it out. Go to the parts house, get a new one, bring it back, and do the whole thing over again, and it is very likely you don't have enough copper tubing left to do it. Okay, so it's like major surgery. A unit that's over 5-6 years old, I don't even suggest replacing the reversing valve. Okay, if the mechanical portion of the reversing valve, not the electrical portion, the mechanical portion of the reversing valve goes bad, it can cost about as much as replacing a compressor. So I have to recover all the refrigerant, basically do major surgery on the unit, and it just isn't worth it. Okay. Guys, I don't want to go through this whole thing, but I really want to show you the inside of a reversing valve while you have it on your mind right now. I'm not going to do this whole slideshow today, but I do want to show you the inside. This is a cutaway of a reversing valve that we cut apart in a shop. Okay? What you're looking at here, okay, you can actually see the sliding component that actually moves in the reversing valve. You see your 3 lines that are coming into the reversing valve, that are at the bottom of the reversing valve. This is the solenoid coil connection. This is where an electronical coil fits over here that makes this all work. But the portion right here is actually my whole control portion. This slides back and forth depending on if the coil is energized or de-energized. This is the little U that connects the different tubes together, and this port is where it bypasses. So if we take a look at the reversing valve, okay, that little slide component is in here. If it's slid all the way over to the right, these 2 lines are connected and the bypass goes that way. If it's slid all the way over to the left, these 2 lines are connected and the bypass goes this way. So everything having to do in the reversing valve is dependent on where this slide portion is. Okay, and again, that little U that you see is caused by that little cap, sort of, that's mounted inside this reversing valve. Reversing valve is a very simple operation valve, but it is actually, it does a lot. Okay, it controls the heating and cooling. So again, when we're in one mode of operation, okay, we're coming this way, and we have a U shape here. Okay? When we're in another mode of operation, the slide has slid over this way, causing my U there, and my bypass is here. Okay, so it all depends on where that little U is that's mounted inside that reversing valve. Okay, so when a valve is de-energized, and again, I'm going to repeat this a little bit tomorrow, but when a valve is de-energized, okay, it's in the heating cycle, unless it's a really old system. We always do de-energized in a heating cycle because we want it to fail in heating mode. Okay, so the hot discharge gas comes from the compressor, okay, and comes through the U and goes to the indoor coil. Okay, the suction gas comes from the outdoor coil and comes through the U to the compressor. Okay, that's in the de-energized or heating cycle. Okay, now, when we energize this, okay, let me come to the one that's energized. That's the heating cycle. Okay, again, a heating cycle, because we're going to the indoor coil. The cooling cycle is basically energized. We've now put power on my solenoid. It's energized. This has moved, and if you look closely, you can see the little thing, the slide has moved from the left to the right of this. Okay, so we now have our suction gas from the indoor coil to the compressor, and my compressor discharge going to the outdoor coil. Again, it's all based on the position of this slide inside here. Okay, so these are the 2 positions when you look at this slide, okay, of the reversing valve. Heating cycle de-energized most often in the newer systems. Cooling cycle energized. Okay, and this is sometimes a pretty noisy energized thing. Okay, in my system, I can hear it down the driveway when that reversing valve energizes before the system goes on. It goes clunk, and you hear it start up. Okay. Reversing valve, again, when you're looking at it, this is a brand new one. You have a solenoid coil that is mounted on the pilot valve assembly, which I'll talk more about tomorrow. Okay, the solenoid coil is what's connected back to my thermostat. There's an O terminal on your thermostat. When O is energized, we're in cooling mode. When the O is not energized, it's in heating mode. Okay? And this is what you get to braze in if you ever have to replace one of these. Can you see what some of the problems with brazing this might be? What's your number one problem if you have to braze this in?
They're too close to each one?
Yeah, getting close enough. What about that coil? What about that reversing valve coil? Is that a problem when you're putting high temperature on something? Coil's wire. We braze at extremely high temperatures. Okay, you have to actually remove the coil before you can braze this thing. Okay, and you have to wrap a wet rag around this whole device. Okay, you take a wet shop rag and you have water close by so that you don't overheat this, what we call pilot valve in here. Okay, you have to really protect this whole assembly against getting overheated. So you're putting very hot flame on all four components of this. Okay, and you're also having to protect this against getting overheated. Copper and brass conduct heat very well. That's why reversing valve changeouts are so nasty to do. It's because of the fact you've got to braze in a very close, confined area and control heat. Any questions on what we covered today? Because I'm not going to go further today. I have a whole, tomorrow's another pretty full day on heat pumps. Any questions? Okay, guys, that's all I have for today. You guys